Cool. Okay. All right, here it is. We are Wednesday. Let's see. We finished up the product rule. Okay, you guys talk to me here. How many thought that was pretty cool?
They're just tedious.
It is tedious. Yeah. And I think a lot of times in calculus, you guys will be lost more like in the algebra of it and the tediousness of the algebra than actually the calculus of it. Because calculus part is pretty easy. Hey, we're getting the slope. That's what we're getting. And all that, what that means. All right, so let me go back real quick here on our notes. We had this little rule, is that right? We we did the product rule, we proved the product rule, right? That whole thing. And the genius stuff was adding in this little extra piece here. I don't know, can you guys see my cursor? And the genius part, kind of genius part was over here of doing the g of x plus h and taking the limit. Okay, so we are here. We did a couple of these guys here, find the derivative here. Almost done, almost done. We got 2 more to go, sort of theoretical stuff, and then we'll get going. So we have the product rule, that's done. So now let's go with the quotient rule. Of course, a function. So question really becomes, don't need to write this down here, but so far we were able to do some of them, right? Remember something like this? We were able to convert it into something like this and still do the power rule, right? The problem comes in when you have something like this now, x squared plus 7x plus 4 over, right? Now we have ourselves some trouble because now those are ratios of 2 polynomials and now you're stuck. So the question in calculus is, can I do that? So let's go back and say, yes, I think we can. So we just need to figure out this. We need to figure out what is the derivative with respect to x of a function on top and a function on the bottom. And we go from there. There's our little fun part to play with. And I don't know, let's put a question, well, let's not put a question mark here. Let's fill it in a little bit later when we do them here. So the proof for it. Let's go with it. Let's use what the book does. It uses j sub x as this little fun piece here. All right, you guys, I'm gonna start it and you guys tell me if I make a mistake or if I tell me if I'm going off wrongly. Of course, there's a little genius part to it as well, just like the product rule.
What's the problem? I feel like I don't know how this for this one and the product rule. It's like I can tell what there needs to be the adding and subtracting, but I can't figure out what's added and subtract. And then like last night I was trying it and I tried a bunch of different things, and then it was just not working. And then my dad's just like, "Let's make it do it." And I'm just not like your son. But I don't know, how do you think of what to add and what to subtract on this or the product?
Sure, yeah, and it's that's why I say it's more of a stroke of genius. It's the idea that pops up and like, oh wow, yeah, that would work. And so are you able to know it, figure out? Not really. I mean, if you look at it for a little while, you might be able to figure it out, but we're just setting up the precedent for it, right? Once we get that, we just use a rule to get the rest of our stuff, right? But I want you guys to try it. This is part of you guys learning how to struggle with it, just like the first people looked at it. They struggled with it too. Like, man, how do I do this? How do I put this together? And the quotient rule, I would say, is a little bit more tedious. And oh, that's me. Sorry, that's my sticky notes. That's my clicking stuff that I shouldn't. Okay. And the quotient rule is a little more tedious than the product rule. So, Sadie, did you try it though? You tried it?
I worked on it for like probably 2 hours, and then I was not understanding it. Then my dad was like, "Oh, you can do it this way, but you don't know that." And so then he had to think through because he knows what the answer to be, and so then he figured out what to add. Do you have time to do that? I didn't have time. That was the problem.
Okay, all right, guys, real quick, don't spend 2 hours on a single problem though, first of all.
Well, I wanted to figure it out, and I was really mad because I thought it should be, I tried adding a bunch of different stuff and it wasn't working.
Gotcha. Okay. No, but good job. Good job on it. I love the fact that you would struggle with it and kind of think it through. That's really actually important to see it here. So, Katie, let's see how far you got, and let's see if we can finish it up. So by definition, right? If that's my function, by definition, j prime of x would be the limit as h goes to 0 of, I think it goes like this, f of x plus h, g of x plus h minus that over that. I think that's the limit function. Boom, I think we're ready to get started. So let's see. First things first, with any complex fraction, and you guys, if you think about it, we're just doing algebra just with function notation. That's all we're doing here. So let's see. First things first, tell me if you guys agree. This be limit as h goes to 0 of, and then we need to simplify that whole entire complex fraction. I think I'm going to write it as one big giant one. Let's see, common denominators would be g of x plus h times g of x. And aren't we just going to cross multiply this way? So it'll be f of g plus h times g of x minus cross, or multiply this way here. Sorry, not cross multiply. And you guys are following along. You guys tell me if I'm good. Those complex fractions, though.
What's first of all? It's g of, so the bottom, the denominator is g of x plus h times g of x. And the top is fx, fx plus h g of x minus fx.
See if you go back into like a algebra class, right? Like 2/3 minus 4/5, right? You would multiply the 3 and the 5 together to make the 15. And then it's the multiplication of the 2 and the 5 minus the 3 and the 4. Are we good? To make 12. That's kind of what we just did just now, just with function notation. You guys talk to me. Are we okay? Does this make sense?
It was just the I think it was just all the g's and the x's stuff.
Yes, that's where it gets a little complicated. Okay, now talk to me here. If you had something like a 7 underneath here in algebra, what would we do with that 7?
You can just bring it up alongside the 15, right?
Yeah, you bring it up here, right? And then you take the reciprocal. So now it's just a multiplier between the 15 and the 7. Are we good? That's what we do in algebra. So this little h is going to do the same thing here. This h comes up. It's a multiplier of 1 over h. So let's see if we can kind of set this up a little bit here. So limit as h goes to 0 of, and now we have this little piece here. It is going to be a little tedious. I think it's kind of fun. It's kind of fun how everything just falls in place.
That's not fun though.
Okay, see if that makes sense. Now the h just became the multiplier, the g of x plus h times g. Are we good there?
But there is
All right, for some reason my speakers are not working very well here. So let me turn up the volume so I can hear you guys, but talk louder if you need to talk to me. We good?
Wait, what did you just say?
Oh, sorry. My speakers are not loud enough. So if you need to talk to me, just talk loudly.
Okay.
Awesome. Okay, the stroke of genius. You guys ready? The stroke of genius is add and subtract f of x and g of x. There's your stroke of genius. Dun, 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 dun. So let's see how this plays out here. Let's see, I got myself the limit as h goes to 0 of, whoa, and I'm not sure if I'm gonna have enough space here. All right, Sadie, was this your same stroke of genius? What else did you try in here?
Well, I had tried a bunch of other stuff, but when I did it with my dad in the end, we did something very different, or something different.
Okay, gotcha. Okay.
Subtracted, let's see. Well, let's get to the end of this problem, then I'll tell you what I did and see if it works.
Okay, awesome. Okay. So let me do this so I can make more space. I'm going to take this to the other page here, just so we can see the more of the transition as we see it. So limit as h goes to 0 of what we had initially, which was, let me go back real quick here. I think it was f, yeah, f of x. Here it is, f of x plus h times g of x. And then we're going to subtract out this, and then we're going to add that in right away. So technically we're not adding anything. And then we have minus, let's see, sorry, have to go back between the two slides here. Minus, there it is, f of x, g of x plus h over that times that times that. Whew, okay. Just love it, especially when you do theoretical mathematics and you're kind of thinking about something and you just start going into pieces, and all of a sudden this aha moment comes up, like, oh yeah, it's just this. And it works a lot of times in mathematics. That's what has happened. Okay, are we good here? So what I see here, and see if you guys see my cursor here, I see f of x plus h over here, minus f of x. Are we good there? That might help out there. Then I also see this little second, the next two pieces. Next two pieces, I see a g of x, then I see a minus g of x plus h. And those are reversed the way I like them. I don't like them that way. And you guys talk to me. So I don't like the reverse right here.
Mr. Antiev?
Yes.
So how did we, because we're adding f of x, g of x, right?
Uh-huh. We're subtracting it and adding it.
How do we put it under the fraction with the denominator of h, g of x plus h, g of x? Because it didn't have that denominator.
Ah, gotcha. Okay, so real quick here. Technically, we added this whole thing onto it.
Oh, with the denominator already there.
Yeah, with the denominator already there. Technically, that's the way we do it. But if you're adding fractions together, right? If you have something that looks like this right here, right? 3 minus 4 divided by 5. If I were to add 7, subtract 7, still under the 5, does that change anything?
It's just that you didn't say when you said what we were going to add, you didn't say it was over that fraction. So
Gotcha. Okay, yeah. So it's inside the fraction piece there. Okay, are we good there with that?
yeah.
Dun, 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 dun. Okay, and so what I see is, I see this. I see the fact that, ooh, you know, maybe I can highlight it. That'd be cool. I like this part right here, f of x minus f of x. Notice that it's that same little piece there. This I don't like. I got a g of x here, then I got a g of x plus 8. So I'm going to flip these around. I don't like the fact that it's doing that. So how do I flip them around? Let's do a few things here. Let's split them off. Let's do it this way. Let's go. So limit as h goes to 0. This I like. This one I'm going to do, I'm going to go like this. I'm going to put a minus sign here. And then I'm going to have this guy go first.
We want to make it into our limit for, we want to make it into g prime of x.
That's where we're going with it. Yep. So everybody okay with that? So I subtracted that piece out and the bottom is still the same, no problem. So I just switched them. So now I like this part right here now. Hey, get away, I don't want you to hear. Thank you. Okay, highlight again here. Now I like it like this. I like the fact that I have a g of x plus h, and then the g of x is right there. I think I can split them now. Let's see if I can split these little pieces now. So I got limit, because limit can split under subtraction. I got f of x plus h, g of x minus f of x, g of x over h, g of x plus h times g of x. There's one split, and I got the little minus sign here. I got the next split, limit as h goes to 0 of, let's see, g of x plus h, fx minus g of x, f of x over h, g plus h, and g of x. Talk to me here after you write it down. See if you guys agree or disagree.
Oh. And then.
All right, are we good there? Look at it, see if you guys agree or disagree.
It's not anymore because you could look at we can make it into the f of x plus h minus f of x. Like you just want that. It's just f of x. It's not like that.
Let's see, thinking to myself now. Oh, you know what? Look at this. This is interesting. Notice the g of x. G of x is here, here, and here. Those can be canceled. Agreed?
Yeah. And then g of x plus h is just g of x.
I think so. Notice the g of x plus h. I could move it out in front now, but also something that we talked about last time. Off to the side here, limit as h goes to 0. If you just have a plano g of x plus h, that's just turned into g of x.
And no, it's not because it's f of x plus h minus f of x over h. So it's f times x g of x over g of x.
And let's see what we have so far at this point then. So then I have, I can scoot the g of x out now. Let's see, so it's gonna be 1 over g of x, limit as h goes to 0 of f of x plus h minus f of x. And you guys keep me honest here. There's that one. This one is going to be, let's see, I'm going to take out a g of x. I'm also going to take out a g of x plus h. So technically, this is the tough part here. Technically, I'm taking out a g of x squared. True or not true?
Yeah.
I got 2 of them. It's the same exact piece there. I'm going to limit as h goes to 0 of g of x plus h minus g of x over h right there. I think I'm there. I think I'm almost there. So this whole piece, the limit of f of x plus h minus f of x over h, that's just derivative. So I have myself a derivative of f right here over g of x right here, minus sign. And let's see, I got a derivative of g of x over here over the original g of x just being squared.
Wait a second. What happened to the, you also need to have that f of x, don't you? Or did we get rid of that somehow?
Sorry, say again.
F of x in the second one after the subtraction sign, g of x plus h, f of x minus g of x, f of x. So that isn't that on the top too, isn't it? Minus g prime of x, f of x over g of x squared.
The g prime of x should be on top, right? It's a multiplier.
One more line. Go up one more line. Another, no, up. Yeah, the f of x there. In the top.
Oh, yes. Sorry. Thank you so much. Totally. Thanks for keeping me honest. There's a f of x right over here. So it should be, let's correct this here real quick. It should be a f of x right here. Duh. So let me write it in a different color just so we have it. So sorry, there should have been an f of x right there. And then there is a f of x times g prime of x right there. Thank you, Sadie, for catching that. Okay, the only thing we don't have here is common denominators. So I'm going to make some common denominators. What should be our common denominator? Yeah, g of x squared. So I guess I need to multiply this guy here by another g of x on top and a g of x on the bottom. That would give me what I want. And I think we're almost done. Let's see. This is going to be f prime of x times g of x over g of x squared. And let's write it as a single fraction. Let's see if this will be okay as a single fraction. Okay, so talk to me here. See if this all makes sense. And I want to kind of hear from everybody. So f prime of x, g of x is what we got from over here. We subtract out g prime of x, f of x divided by g of x. So very similar to the product rule. It's the derivative of the first times the second. Now it's a minus sign, so it's minus derivative of the second times the first, all over the second function squared. And that's just the way the numbers work out. And it must be true because we followed the formula all the way through. So derivative, the quotient rule, let's bring it up here real quickly here, just so we know it now. We know the quotient rule to be let's see, derivative of the first times the second minus derivative of the second times the first, all over, we say the second function squared. There it is. There's our quotient rule now. I think we're ready. I think we're ready to do quite a bit of stuff here.
Mr. Idea,
Yep.
the way that I did it, I got the same thing, but what I did was I made the denominators for the first section of g of x plus h squared from the beginning, and then what I added and subtracted was f of x times g of x plus h all over g of x plus h squared. And That ended up working out the same way.
Oh, interesting. Sadie, if you can, if you have some time, could you take a screenshot of it and send it?
Yeah, I can show you.
Yeah, it would be cool to see. There, I think this is the most easiest way to see it here, but yeah, I should also. I'm curious to see if that works. Okay, we got our quotient rule, we got our product rule. Awesome. We'll go one more rule, and we'll get going here. So we have product rules, but products, remember, sometimes are not just 3 times 4. Sometimes they're 3 times 4 times 5 times 6 times 7. So we do have the extended product rule. And let me just give it to you, just so, because we can work on some other stuff here. So it kind of goes like this. It has 3 of them, but you can extend it out to 4 to 5 to 6 to 7, however you like here. So let j of x be equal to f of x times g of x times, and then let's think of another letter. Normally we just use h. So h is our function here. So this is the extension of the power rule. So if we had 2 of them, the power rule just works as derivative of the first times the second, but then we have 2 of these guys here now. So it's this one plus, and what happens, just to keep things in order, what we normally keep, we keep the functions in order this time. So what we do is we take the derivative of the second one plus, I'm running out of room here, and then we just keep on going, give the first 2 functions the same, and then take the derivative of the third one, and you can see how this is gonna keep on going here. So if you had 4 things you're multiplying, we just keep the 3 functions the same, take derivative of each one. Super cool, super awesome. The proof for it comes off of the product rule, but we won't go in there yet because I want to get to some problems here. So let me see which problem we're on. Anybody know what exercise problem we're on? 1. I think we're on 2, is that right? I'm gonna go with 2. So find the derivative. Let's see. I'm going to name some functions here. I'm just going to call this m of x. M of x is 3x plus 1 over 4x minus 3. That's cool. So I'm going to, everybody okay with that? You guys go start on the derivative already if you like. This one clearly needs a quotient rule here, right? There's no other way to do this. So think back to our quotient rules. We have ourselves, let's see, I think it's the derivative of the first and what some students tend to do in the past, which is probably a good idea here. These are pretty easy rules here, but what they'll do is they'll go over here and they'll take a derivative of each one. What is the derivative of 3x plus 1 anyways?
Would it just be 3?
3, I go with that, yep. And then the derivative of 4x minus 3.
Is it 4?
That's 4 would work just fine, yep. All yours. Can you guys do the quotient rule on this guy? All right, so I got derivative of the first times the second. We got that right there, derivative of the first times the second minus derivative of the second times the first over the second function squared. All right, so the question comes up is, do I simplify this? Do I not simplify it? Depends what the back of the book says. No, in this case, this one probably would be a good one, easy one to simplify, and you're done. Sometimes they do get so complicated that you're not going to simplify unless you really need to. Plus, it's really more of a practice of just doing the denominator, doing the derivative, sorry. But for this one, let's go for it here. Let's finish it up. Simplify it as much as you can, please. All right, I'm going to try to do it on my end as well. Let's see, 12x minus 9, 12x, what is that, minus 4. Hey, this one simplifies pretty easily here. Boom. Negative 13 on top, is that right?
It's not negative 20. No. Oh, there's a 20.
Okay, talk to me, see if that what you guys got true.
Yep.
Okay. Okay, fairly easy one just to get us started here. Let's try. Try a little bit more complicated, not by much.
Wait, how do we know we're done there?
How do you know you're done? You've taken the derivative and then you've simplified it, and that is about as much as you can get.
Okay, so we don't want to expand out the bottom and then try to do anything with that.
No, no need to, because there's no way you can. We only generally do that if we want to cancel with something. But if you want to cancel something, you still want to keep it in factored form to cancel stuff out anyways.
Okay.
Okay, so all yours here, beginning to end. B, let's see, I'm going to call it what? Call it case of x. Let's see, 5x to the third. This would be x squared. Boom. All yours with that. So from beginning to end, give you guys a minute here. Try it yourself. Half an hour, yeah, really good. All right, I'm going to do it on my screen as well. So look up if you're stuck, otherwise keep on going. All right, in this case, this one, unless we really need to simplify it, I would not even simplify it. I would just keep it as that's the derivative. If we need to do other stuff with it, that'd be fine. But some of these are just practice of taking derivatives. That's what you want, sort of, to get into this. Okay, did well. Talk to me here. Eli got it right before me. Cool. Sadie, Kate, Taya got it before me.
Yep, I just have to write it down.
Okay. Okay, so let's get into some problem. Oh, one more, I guess we should do real quick here. I'll go with exercise. Can you talk to me if I need to go back here? Exercise 3. Actually, no, we could do C. Let's do letter C. I just want to try this one real quickly here. This one's Z of X. This guy here. And so Eli and Taya, since you guys are on the left side of the page, you guys going to do this by the product rule? Sadie and Kate, we're going to do it by the quotient rule. Just want you guys to realize the fact that, yes, if you manipulate the function itself, you can use a different rule to do it. If you simplify stuff, you can still do it that way too. So. All right, I'm going to start it myself as well. So let's see, good too. So don't look up at the board unless you're stuck. A little manipulation needs to happen here. Sorry, it's not even a product rule. It was just a power rule at this point, right? Eli and Taya. Let's you do that.
So what is the derivative of x squared?
You can just do it, well, I guess we can do use power rule, like, use this rule, and do the, power rule. Use it.
They talk to each other just to make sure. Eli and Taya, you guys are good on the same page? That makes sense there? Kate and Sadie, are we good talking to each other, even if it's through masks? So that becomes a 0 out there. This becomes a 12x over x to the fourth. And then simplifying a little further, we got ourselves the exact same thing. So a little manipulation up front. You could use different rules to get where you need to get to. This one, I should power instead of product rule. Okay, still same answer, right? Boom. Okay, so let's talk a little bit about something here. Just an example here, and then we'll get going with what we need to do here. Let's talk about pain medication is pretty cool. Pain medication. Whenever something enters into the bloodstream, particularly pain medication, it usually takes about 2 hours for it to be in a full effect, at least in the older times, pain medication. And so what happened, let's say this is the amount of pain medication in your bloodstream over time, right? You just took it. So it starts off about right here. You didn't have any before, so it's 0, 0, right? You take it, it comes into your bloodstream. And then what generally happens is it goes like this. And then that's why, generally speaking, if you got your wisdom teeth out, they'll say, hey, take Excedrin every 2 hours until pain goes away or something like that, right? Or every 4 hours nowadays because it's a little stronger. Okay, we good. If we were to do a slope formula, if we were to do a slope formula from here to here, notice that would actually just be 0. Is that right? Slope is 0 right there. So if we were to do this non-calculator, we calculate this and say, oh, nothing changed. Nothing changed from the first point to the second point because we have a slope of 0. And the only question is, did something change? Absolutely something changed, right? We hit a peak somewhere in the middle there, right, of the medication, and then it went down. And so this little piece here, that's why algebra doesn't really get us to what we need to get to. It doesn't get us to finding more information about this here. And so if we think about a few points here, what's the most important point here? Or what do you think is the most important slope to sort of see? I'm thinking this guy right here, this is an important slope to see. As far as pain medication is concerned, what does this mean right here? What's this point mean right there?
The amount of pain it's alleviating at the height of its where it's working.
Absolutely. We just, yes, the maximized amount of pain medication in the bloodstream, right? After that, it goes down. So slopes of 0 in calculus, they are important to us. Because that means it hit either a maximum value or it just hit a minimum value. So if you're in business, you just hit your minimized costs, or you just maximized your profits. So this little maximum and minimums are really, really important here. And so that's what we're going to try to find. We're going to try to find these guys here. Sometimes we do want to know just when is the pain medication increasing at a certain rate. Maybe if pain medication increases too fast, it does something to the body. So we're like, okay, no, we got to be careful. It doesn't go over that much. We're good? Or that fast. And so let's go with it. We're going to try to find these guys, and we're going to try to find these guys in general. So how about number 3? Number 3, here's what we're going to do. We're going to try to find where is the, okay, I can't spell here, there it is, horizontal tangent line. Where is the horizontal line, tangent line for this function right here? So this function is measuring something, whether it's pain medication, whether it's the distance that something is being flown by, and that distance would be the maximized distance away from an object or the minimized distance away from an object. Just to give you guys a graph illustration, what this kind of looks like, I just at least want to show you. X to the third minus 7x squared plus 8x, it's going to go like this. It's going to come across here, goes like that, comes back down, and then it comes back up like this. So we're going to try to find those spots. So what are we trying to find? We're trying to find this dot here, approximately, whatever that is, because it has a slope of 0 or has a horizontal tangent line. That's what we talk about. The tangent line meaning it's touching this function right at a single point, and it's horizontal, which means it has a slope of 0. So all yours, go. Think about what you're going to do. All right, any takers? Or are we already done? Eli, are you done already?
How?
Thinking, okay, gotcha. So our concentration is to figure out the slope of being 0, right? But hold on, isn't derivative really the slope at every single point?
We just need to find the derivative.
So if we take a derivative, we're going to get a formula that's just in terms of slopes only, right?
Plug it in for 0.
And set it equal to 0. I think I like that. Yep, let's go with it here. So find me the derivative of this guy.
Let me just break it out.
So that's minus
And what is the derivative here?
Can we just use the power rule and split up the limit into all the different sections?
Oh yeah, absolutely. So take the power rule individually of each of these pieces. And so x to the third becomes 3x squared. Minus 7x squared becomes minus 14x. And how about a plus 8 at the end? Are we good there?
Yeah.
That's perfect. I think we're good. Okay, so we got the derivative. Now let's do one step further. We're trying to figure out when the slopes are 0. So we're going to disattach it from our function. And we're going to set it equal to 0 or whatever
Oh, okay.
whatever slope I want. In this case, I want it to be 0 because I want the horizontal tangent line. All right, have to help me out. This is why we did factoring in algebra. What does this guy factor into?
Last two.
Cool, okay. I need a 3x and an x to get 3x squared.
Oh, here, it's 3 times 2 is 6, and then 4x, and then 6 minus, oh wait, what are we doing?
And it has to multiply to get 8, and to get 14. Right?
Yeah.
So that's
Oh, it doesn't, yeah, it doesn't.
See, to get a positive 8, we need a minus minus, right? That's for sure. Minus minus to get a positive 8 because we have a minus 14. So our choices are 8 times 1 or 4 times 2.
Oh, because there's a 3.
Yeah, we just don't know how to do algebra 1.
if we had written it down, we could have, but try to do it.
Yeah.
Trying
Okay.
to be lazy.
3,
Is it 3 minus 2 times x minus 4?
I'll go with that. Okay, perfect. Okay. So let's split them off. Set equal, each of them equal to 0. Boom. This minus 4 equals 0. Let's see. So add 2 divided by 3. I got myself a 2/3. And then add 4. I got myself 4. And I think I got it.
I like that.
So that's cool. That's in terms of, let's see. In fact, at the 2/3 marker, if this was a business transaction, right, that means we've maximized our profits at 2/3. So whether it's a price, maybe it's, let's see, selling something for 67 cents. If it's maximizing storage space, we fill up storage space at 2/3 capacity, and now we'll maximize storage space because of costs. All these little different things comes up. The minimize cost comes in at 4, right? So if you want to minimize costs, it'd be 4. If you're talking about 2 planets coming closer together to each other, that means the closest they get happens at x equals 4. And then you want to figure out the distance between the planets. That's something that we do with what I could think the meteorite, big humongous meteorite that passed by like 13 years ago. We had to figure out if it's going to hit Earth's atmosphere or not, it kind of came sort of close. But all these things, are we good there? Is that pretty cool? I think that's pretty cool. Okay, so that's the horizontal line, tangent line, but let's go a little further. What happens if we don't want to just figure out the max or the min? What happens if we want to figure out a certain amount of change that's happening? So
You can just set it equal to that number instead of 0.
Oh, we want to
you got that number, and let me find it here. Assign the values, da, 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 da. So here it is. Find.
Yeah, that's right. I'm on example 6. I'm on example 5. Oh gosh.
Are we on example?
No, we're just not.
We're all on different examples.
Yeah. I continued from what I had before, which may or may not have been correct, but I kept. You just didn't do A and B, Kate, so then you kept. Oh yeah.
Okay, so getting off the horizontal line, horizontal tangent line, I want to figure out where this guy has a tangent line parallel to 2x plus 3.
Would it be 8x minus 3 that equal to that?
But 8x minus 3 can equal 2x plus 3.
So you guys talk to me, what you guys do? Take a derivative, hopefully, of fx first.
Wait. Oh, wait a second. I think it's where x equals 1 in my heart.
If it's parallel to it has the same slope. So, right?
Yeah.
All right, talk to me louder. That's-
Can't.
Do we set that equal to 2x plus 3?
Wouldn't the slope of 2x plus 3 equal 2?
Yeah.
So then
but the
it's
slope of
two.
8x minus 3 equals 8.
But that's not the slope, that's the derivative line. Wait, is that? I don't know.
This is cool. This is from algebra here. If I just want something that's parallel to this line, what's the only information I want out of this guy?
I didn't hear that.
The slope.
I just want the slope out of it. That's it. Because if I'm trying to do something parallel to 2x plus 3, right?
5/8.
Everything is changed differently except for that slope. Slope still has to be a 2. So when we take a derivative, all we do is we stick that derivative equation equal to the slope that I want. So how about adding 3 to both sides, dividing by 8, and how about I get myself an x equals 5/8?
Yeah, maybe. Well, actually, if we had just taken everyone look at their last class, we would have been better than all these two.
Yeah.
We knew that they had the same.
So that's cool there. Let's see, another thing is in mathematics, a lot of times, or in real life, we have functions that set on top of other functions here. So in economics, maybe we have, let's say if you're looking at a function that incorporates usable income from 1900 to now, right? You have a function that has gross income of all the people, right? Subtract off, then you have taxes that year for each person, right? So you have one function that's actually in terms of 2 other functions. Are we good? That happens quite a bit in mathematics. And so this one, let's try this little piece right here. So this is called combining functions and derivatives. combining. Is that right? Combining. Combining functions and derivatives here. And just real quick here, then we'll do A and a B here. So let's see, I'm going to make this case of x is equal to 3 times h of x plus x squared g of x. So just find the derivative. So I have a case of x or k of x, and I have variables inside here. That's true. They also have extra functions inside here. There's a h of x inside there. There's a g of x inside there. So I want to get the derivative of this.
It's just 3 h
And talk to me, see if you guys at least see some two product rules sitting here. Sitting here possibly.
It's constant multiplier and power, and then just adding.
Yeah, can we just make it,
Can we just split it into like the constant multiply, or split it into two limit, like taking the limit of both separately, and then do like 3 limit h of x is h equals 0, different h's, and then 2x limit g of x is h equals 0.
I think you're making it more difficult because you don't want to go back to limits. You just want to go back to your derivative rules again here. So the question is this right here. Is that just one single piece? Is there anything multiplication that we need to deal with as far as derivatives are concerned, or are we good here? What's the derivative of h of x?
H of x.
H of x, h prime of x, there it is, all done there. This one now requires a product rule because notice you have an x squared on your hands and a g of x.
2x times g.
Let's go with it here. What derivative of the and you can split it down the middle here. First function is x squared, right? Our second function is g of x. So derivative of the first times the second plus derivative of the second times the first. I believe that's the way it goes. Right, so if we were looking at, again, usable income, just real quick here. From 1900 to 2000, let's see, in the US usable income, and we had a function that was there, right? That function, I'll put U for usable income, is gross income subtract taxes, right, per year. So that's kind of what gives me that. That's just a real simple one, but there it is. So if I take a derivative of this, I'm going to see the changes from year to year, right? Because it's going to be a slope formula now in my hands. So that's a totally different information that I had before. Now I have what year did it jump the most, right? What year worse or better, right? So I'm looking at slope from year to year at that point. Or which year had the highest increase of usable income, or which one had the highest increase or the highest decrease of usable income when the taxes start going higher. All the good stuff here. Are we good there? So we have functions that are actually inside other functions here. And one more, let's go into physics. Let's jump into physics for all you physics guys here. So first things first, we should note before we get started, and the book just kind of just briefly touches upon. So Eli, you have to help us out here. Eli and Taya, because you guys are both in physics here. We have a position function. And so if you know a car is traveling down the road, its position is given by this equation. If you were to take the derivative, and this is what we call you guys take physics classes, and in college, there's a distinction between calculus-based physics and non-calculus-based physics, because this is the little piece right here. You take a derivative of position, and what you have is you have velocity. So you have, technically it's speed plus direction. That's what velocity is. And then what you do is you take a derivative again. And you got yourself your acceleration. How fast is it increasing, or how fast is it decreasing? Let's see where we're at. We're 38 after. Okay. Yeah.
Do you take calculus-based physics with only 1 year of calculus? Like a low-level version?
Here, I think you take it after your first year, I believe. Yes, for the calculus-based physics. At least when I was in school, that was like so many years ago. But I believe it's just the first year, after your first year, because you're just taking derivatives. Okay, let's go with it here. I have a car driving along the freeway. And its position is given by S of t. And Eli and Taya, do you guys use S for position, or do you guys use something different?
We're doing conservation of energy.
Okay, gotcha. Okay. Okay, we're gonna get really physics here. Meters per second is what we got here. I got two pieces for you here. So first things first. When is the, that would be clinical. Velocity of the car 0. When is the velocity of the car 0? And this is kind of tricky here. If that's the case, determine the acceleration. When velocity is 0. Okay, so when is the velocity of the car going to be 0? And in that space, in that time frame, determine the acceleration when the velocity is 0, which is kind of strange. You think like, hold on, it just stopped, didn't it? And technically, no, because you can have acceleration going the other way. We'll talk about it when we get to position functions here. All yours. Talk to me. What should we do? We've got about 4 minutes left. Let's jam with it.
Set that equal to 0.
Yep. We take this function here.
Minus 3 or 2 minus 3. Times what? 3 minus 3 times 13 minus 3.
And you could label it as S prime of t, or you can label it as V of t, because you're moving from position to velocity here. So whichever way.
Oh,
You could do like that, or you could use S prime of. Either one is correct. Either one is just perfect. You're declaring the same thing when you do that here. Once I took the derivative, that's perfect. Then I start setting it equal to 0 to figure out my answer here.
1 and 3.
We're going to be the acceleration.
I think that's what I heard. Take the 3 out. Is that right?
oh yeah.
You can factor the 3 just to make things easier.
Oh,
divide out by 3, so I don't have to mess with that again. And factor this guy out.
Oh, it should be the same. Unless we made some -1 and -3.
Okay, boom, 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 switch it around, and I got myself my 2 answers, right? Time is equal to 1 and time is equal to 3. So talk to me here. When I have velocity is equal to 0, what is happening at 1 and 3? What's going on with the car?
That's when velocity
The
is 0.
velocity is 0.
When t equals 1 and t equals 3.
Yeah.
Yeah, but which means what?
Acceleration is also 0.
Ah, that's the interesting thing is, I wonder if acceleration is also going to be 0 or not. But at 1 and 3, because velocity is 0, we do have to see if there's a sign change. And if there's sign change at 1 or before 1 to after 1, and then before 3 and after 3, we know the car changed direction. That's what velocity is going to mean at 0. So this car changed direction, is going left and then went right. Or the height, if this was a rocket, right? The rocket went from up to going down. Okay, so let's see what happens here. I got time is equal to 1, time is equal to 3. Let's take the next derivative. We got about a minute left here, so let's go with it here. So let's take the next derivative. That's going to get us to acceleration. And I got myself 6t minus 12. Is that agree? Agree with that?
16.
But then at that point, what we're going to do is we're going to take and we're going to plug in acceleration.
60 minus
Still
12.
not seeing that. Oh, you took the derivative. Oh, I see. You took the derivative of this. Yeah.
But the derivative of s of t.
No, he took the derivative of the derivative. He took the derivative of s prime t.
Oh. Okay.
Okay.
Okay, I get it.
It's not the whole. It's not the point. It's not x. It's the derivative. Because those points that we
Yeah.
have are x.
Yeah, so taking the derivative.
Okay, good there. At that point, we're going to plug in the 1, right? Because we want to know what's happening at 1 second. Right at that single second, we have a decrease of 6 meters per second. So let's see. I'm thinking if that's the case, this car at 1 second, it went from going up to going down, or went from going right and then started to go left. Are we good? It changed direction on us. That's because the acceleration was going down, 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 right? Acceleration was going the opposite direction here. And then at 3, let's check out what happens at 3. 3 times, or 6 times 3 minus 12. That makes 18 minus 12, which makes 6 meters per second. And actually, it should be squared, because you're talking about acceleration here. In this case, at 3, the acceleration is the exact opposite. It's actually a positive acceleration. So that means the car, instead of going left, it turned to go right at that point.
The car is accelerating. So.
And it started going right afterwards for the rest of the time. Okay, are we good there? Does that make sense? At least a little bit here. All right, we didn't get to Newton's law of gravitational pull, but that's fine. I think we can. Oh no.
Wait, can we do it on Monday?
Wait, wouldn't it be 2 because we need to divide by the 3 that we multiplied to a?
Huh? It's not multiplied. It's a of 3.
Oh, got it.
All right, we are a little bit over time, and I don't want to see Ms. Bear wait for us here.
You guys have physically to stay here.
Yeah.
So we're gonna stop there. Maybe we might just do the gravitational pull problem on Friday, and then we'll go on to 3.4. So 3.4 for next time. It's going to be derivatives as rates of change. I think we can squeeze in that gravitational pull.
Wait, Ms. Mangia,
I am so.
you just said Friday, but we don't have calculus on Friday, but we should have calculus
No,
on
we
Friday.
shouldn't. No, we shouldn't.
Yes, we should.
Then- right. Okay, pause. We'll be there on Monday. We'll continue this fun stuff on Monday. So you guys have enough stuff to do 3.3 homework at that point. All yours, have fun.
Is that your
Thank
one?
you.
Uh-huh.
Oh, we're a little bit different because I just have one class from 9 to 9:45. Then I have to figure out what time to break. And then I come back to my lab. You go home? I sometimes go home, but I'm
Thank
trying.